Hi guys, so today we're going to look at inverse variation. So inverse variation is going to be very similar to something you did in Algebra 1 that was called direct variation. In fact, we're going to do a very similar process, but our operations are actually going to be flipped. Now, direct variation was what we talked about back in Algebra 1. So what you learned is that if something varied directly, if there was a constant that tied those variables together. To find that constant, we did y divided by x, which was very similar to the concept of slope. So once we knew what k was, we could write an equation that related y to x, which looked like it was this form where k was that constant. Again, it looks like a linear function where k is your slope. But what's specific about this line, it can't just be any line for it to vary directly. It has to be a line that passes through the origin, because if you notice, there is no y-intercept to that line. It is just a slope times x. And then the last thing about direct variation, if you had a table of values, if you want to see if it varied directly, what would be true there is that the quotients in that table, so if I did y divided by x, again, very similar to slope, that value would be constant throughout the table, and that's a way we could tell if those points were varying directly. Inverse variation, very similar, except our constant, instead of doing y divided by x, our constant is found by doing x times y, which means my equation then is going to be k divided by x. And now what this would look like then as a graph, this is actually going to be a pretty good introduction to rational functions, because that's similar to what our shape's going to look like. And then just notice your end behavior there. As x approaches infinity, y is approaching 0. And as x approaches 0 from the right side, y is approaching infinity. And these are just talking about if we're looking at positive values like real-world situations. Then if we're looking at a table of values, the products in that table would be constant. Again, that's because the constant's found by multiplication. So let's look at an example here. We're going to figure out if these relationships are a direct or inverse variation. So I think the easiest way to do this is to solve for y. And then from there, we can look and see what our equation looks like and which equation it matches up to. So on this first one, I'm going to divide both sides by x. And if you look, this looks exactly like our inverse variation. Okay, where k would be 5, and this would be an inverse variation. All right, look at b. Now this looks similar to our direct variation except for this -4. But think about what you guys know from Algebra 1. -4 would be the y-intercept, which means it does not pass through the origin. And direct variation has to pass through the origin. So this one is actually going to be neither. Then my last one, to get y by itself, I'm going to multiply both sides by 2. So I get y equals 2x, which is direct variation. The constant there would be 2. Again, table of values, what we're going to do is we're going to look at the quotient of x times y. If that's constant, it would be an inverse variation. Direct variation, we would look at y over x. Again, think about lines, think about slope. It's y over x. So if I were to multiply these values together, I do not get the same thing. So this is not an inverse variation. If I do y divided by x, though, every time I get the same value. So this table does represent a direct variation with x and y. Again, if you were to plot those points in a graph as well, that could help you. You could see that it is just a straight line that does go through the origin. All right, then let's look at this next one. If I start by doing x times y, every single time I get 60. So I don't even need to check the other option. This is an inverse variation. And again, look at your graph here. So 160, 230, 320, 415. It's going to follow that same pattern as well. All right, so now let's look at some algebra examples. So what we're going to do is we're going to find these values given some information. Now what's important here to pay attention is it tells us if it varies directly or inversely. So if it varies directly, remember that's like slope, that's like a straight line. So my constant, again, which is like slope, is y divided by x. Okay, so if y is 3, x is 6. So that's 3 over 6, which I can reduce to 1/2 if I want to. That is my constant of variation. So now if I want to solve for that, I can set up an equation if I want. My equation would be y equals 1/2 x. And then I can use that equation to find anything. Specifically, this wants me to find what is y when x equals 8. So all I would do is plug in 8 for x, and I get that y is equal to 4. All right, and then if y varies inversely, okay, again, let's find our constant first. Okay, so these are the same x and y values, but my constant this time is x times y. That means my constant here would be 6 times 3, which is 18. All right, my equation also looks different. It would be y equals 18 divided by x. All right, so I want to know what is y when x is equal to 9. So again, just plug in 9 for x, and I get that y is equal to 2. All right. So now last thing we're going to look at is just a couple of word problems. Very similar process to what we just did, but we need to find what our variables are by reading the problem. So example 4 tells us, Kim lives in a suburb and drives to work in a city. The time and hours it takes her to get to work varies inversely with her average driving speed. Okay, so what I'm going to do is inversely, which means my constant is going to be x times y, or in this case, t times s. Okay, so her speed varies inversely with her time to get there. So it tells us she averages 20 miles per hour in heavy traffic. If that happens, it takes her 1.5 hours to get to work. So let's find our constant of variation then. So then it's going to take her 1.5 hours to get to work if her speed is 20 miles per hour. So that gives us a constant of 30. Then we can use that constant to find my answer here. Now, to make this a little bit easier, I'm just going to use the same equation that I had before. So k is equal to t times s. Well, now I know k is 30. And let's look at the information it gives us. It says, how long would the trip take if her average driving speed is 50 miles per hour? So we're trying to find the time if her speed is 50. So then all I would need to do, solve for t, is divide both sides by 50. So t is equal to 3 over 5. So that's 3/5 of an hour. So if we want to convert that, we can. 3/5 of an hour. We would do 3/5 of 60, which would be 36 minutes. All right, again, with inverse variation, just remember, what's nice about these, if you think about these, again, as a graph, inverse variation, the graph looks something like this. So as one variable, as my x is getting bigger, my y is getting smaller. So look at this case. It took her, if her speed was 20 miles per hour, it would take her 1.5 hours to get to work. Whoops, put my dot in not a very good spot. 20 miles per hour. Here's, let's say 1.5 hours is up there. If her speed is 50, okay, it's taking her less time, which also just makes more sense as an actual real-world problem. If you're driving faster, it should take you less time to get to work. So again, 20 miles per hour, an hour and a half, which is 90 minutes. Okay, 36 minutes when we're going faster. All right, last example. The time and hours it takes a group of volunteers to build a playground varies inversely with the number of volunteers. So K is equal to T times N. It takes a group of 10 volunteers 8 hours to build a playground. So my constant then is going to be 8 hours times 10 volunteers, which is 80. So 80 is going to equal t times n. And then we can use this to find any information we want. It wants to know how long it would take 12 volunteers to build a playground. Okay, so we know my constant is 80. I don't know the time. I do know that the number of volunteers here is going to be 12. So divide both sides by 12. And then I'm going to get 6 hours, and then I'm going to have some minutes left over. So 12 times 6 is 72. So I'd have 8 over 12 as a remainder. So I need to turn that then into minutes. Okay, so 8 over 12 times 60, and let me go ahead and reduce that to make it a little easier. So this is 2 over 3, so 2/3 of an hour. So 2/3 of an hour times 60 gives us 40 minutes. So this is going to be 6 hours and 40 minutes. And again, it would make sense here. Okay, more people, it's going to take less time. Okay, 10 volunteers, 8 hours. 12 volunteers. Okay, again, more volunteers you have, the less and less time it's going to take. And again, if you think about it, it's never going to take a 0 in that time. So even though this is going to get closer and closer and closer, it still has to take some time to make that playground. Even if it's 100 volunteers, it's still going to take something. It can't just magically appear on us. But that concept is something we're actually going to look at when we look at rational graphs, which is going to be the next thing we do tomorrow.
All right, so now we're going to transition and we're going to start looking at the rational parent function. Now today, we're really just going to get into an introduction. We're going to look at some of the pieces, some of the characteristics, and we're going to look at transformations. Now, kind of similar to polynomials, we're going to look at transformations today, but the transformations for this function are not the most frequently used way to graph these rational functions. We're going to look at a more detailed approach to graphing rational functions on Friday, because today it's really only going to help us graph the simplest rational functions. And the more complex rational functions come up a lot more often, so we're going to use the process on Friday a lot more than we use this one. So a rational function, think about a rational number. A rational number can be written as a fraction. A rational function is a fraction, but specifically it's a polynomial divided by a polynomial. Remember, a single number is a polynomial. So like 3 over x squared could be a rational function. What is not a rational function? 2 to the x is not a rational function. So you will not see that as it's not a polynomial. 2 to the x is not a polynomial, so you won't see that in part of a rational function. The square root of x is not a polynomial. Let's see, we talked about x to the 3/4. You have to have whole numbers. Another one that is not a polynomial would be the absolute value of x. Because if you remember, we said those polynomial graphs don't have any sharp turns. So that absolute value comes to that sharp point. It's not a polynomial. Those polynomials always had those nice smooth curves on them. So polynomials are, your quadratics, your linears, and then, any other combination of just your basic normal terms. That could be the denominator or numerator for a rational function. All right, so let's look at what the rational parent function looks like. So we'll start by plugging in some points. So I'm going to start by plugging in 0. Well, if I plug in 0, my graph is undefined. So I don't know what that tells me. So what I need to do is figure out what's happening close to 0. So I'm going to start by picking some points and seeing what happens as I get closer to 0 from the right side. Well, if I plug in 1, I'm going to get 1. Okay, well now let's get closer to 0. Let's try like 0.0, or let's do 0.1. 1 divided by 0.1, that's like 1 divided by 1/10. That gives me 10. All right, well, let's get closer to 0. Let's do 0.01, 1/100th. 1 divided by 1 over 100 is 100. Let's do 0.001. That would be 1 over 1,000, which is 1,000. So those x's that I'm picking are getting closer and closer and closer to 0. And as I get closer and closer and closer to 0, those y values are getting bigger and bigger and bigger and bigger and bigger. but they're never actually going to touch 0 because my graph is undefined because I can't touch 0. So that's showing us the right side of 0. Well, now let's look at the left side. All right, let's start with -1. Well, 1 divided by -1 is just -1. Well, then let's get closer to 0. Let's do a -0.1, -1/10. So 1 divided by -1/10 is -10. Then let's do the same thing, -0.01. That would be -100. -0.001, -1,000. So as I get closer and closer to 0, those y's are again getting smaller and smaller and smaller. And that is how I know that there's an asymptote at 0, because my graph is approaching infinity. Now, it doesn't matter that one's approaching infinity positive and one's approaching negative. They could go in the same direction. They could go backwards. We'll look at transformations and some things today and on Friday so you can see how those change. But what matters is that as your graph gets closer to that asymptote, the y's are going towards infinity. All right, so now let's talk about the end of this graph. All right, so let's talk about as my x's are getting infinitely bigger, what's happening to my y's? Well, if I plug in 1, it's 1. If I plug in 2, it's 1/2. 3 is 1/3, 1/4, 1/5. So those fractions are getting smaller and smaller and smaller. If I keep going, I'd have 1/10, 1/100th, 1/1000th, 1/1,000,000th. Those fractions continue to just get smaller and smaller and smaller, and they get closer and closer to 0. They don't actually touch 0, but they get closer and closer to it. All right, let's look at the negative side. Again, -2 would be a -1/2. -1/3, -1/4, -1/5, -1/6, -1/10, -1/100th, -1, you see the pattern. Again, getting smaller and smaller and smaller, but not quite getting to 0, just getting closer and closer to it. So that shows us that we have a horizontal asymptote on this graph. So that horizontal asymptote shows the end behavior of your graph. So vertical asymptotes occur because we can't divide by 0. You actually cannot touch that point. So you will never touch or cross. So again, we can't divide by 0, so that's why we have that vertical asymptote that you can't touch. Horizontal asymptotes are different. Now, the ones we look at today, most of your graphs are going to have a similar kind of shape to them. But as I said, when we get into the more complex graphs on Friday and next week, you're going to start to see some very different things happening with these graphs. And because the horizontal asymptote is just showing our end behavior, it's not something that you physically can't touch. So you actually can touch and cross a horizontal asymptote. So we'll see more examples of that on Friday. All right, so now let's just go back and review all of our vocab, domain, range, and all these other intervals. Domain here looks a little bit different. So left to right, -infinity, then it stops. It does not touch that vertical asymptote. Then it continues, and then it keeps going to infinity. Range is bottom to top, so our lowest y value is -infinity. It keeps going until the y value of 0. It picks back up at 0, and then it keeps going until infinity. Increasing intervals. Well, let's look at our graph. So as our x's get bigger, well, that first section of the graph, my y's are getting smaller. That second section of my graph, my y's are also getting smaller. So this graph is actually decreasing everywhere. Now, we're going to write it as 2 intervals because at 0, nothing's happening, and it's not decreasing from -1 to 1. So we just write those 2 separate intervals. And this graph does not have any increasing intervals. If you remember, positive intervals, that is where we list the x's where our y's are positive. So this interval right here is where my graph is positive. So that is from -infinity. Oops, sorry. That is from 0 to infinity. Negative intervals would be when, again, my y values are negative. So to list that interval, that would be from -infinity to 0. Symmetry on this graph, this is actually an odd function. Remember, algebraically, if I evaluate f of -x, I get a -1/x, which is negative f of x. So this is an odd function, which means it has origin symmetry. Asymptotes we already talked about. This graph has a vertical asymptote at x equals 0. And there is a horizontal asymptote at y equals 0. Now, whenever you write your asymptotes, you need to make sure that you write them as lines. They are equations of lines. So we do need to say x equals for vertical, y equals for horizontal. All right, end behavior, a little bit different than what we've seen so far. So as x approaches negative infinity, let's see what y approaches. Well, as my x's get smaller and smaller, my y's are actually approaching the horizontal asymptote, which is 0. As x approaches positive infinity, it's the same thing. My y's are approaching that horizontal asymptote, which is 0. Now, in addition to end behavior, we're going to look at something else. And this isn't really the end behavior of the graph, but we do want to kind of talk about what's happening here and here. The reason we kind of want to start looking at that is really end behavior is getting you guys ready to write limits when you get into calculus. And while this isn't an end behavior, it is something you'll probably see once you get into limits. So what we're going to look at is what happens as x approaches that vertical asymptote. The problem is it's approaching two different values based on what side of the graph you're looking at. So we can specify which side we're talking about by putting a little plus or a little minus up there in the corner. That little plus means as x approaches 0 from the right side. So if I look at the right side of 0, well, the right side of that graph, as I get closer to 0, is approaching positive infinity. Then I can look as x approaches 0, I can put a little negative. That means the left side of my graph. Well, the left side of 0, as I get closer to 0, those values are again getting smaller. So y is approaching negative infinity. All right, so now what we're going to do is we're just going to look at some basic transformations. Again, we're going to keep these pretty simple today. The way we graph these functions today is going to be different than the way we're going to graph these in the coming days, because the ones we look at in coming days are going to be a little bit more complex than these. So transformations, remember, if it's near the x, it's horizontal. So x plus 2 is going left 2. Minus 3, that's your vertical, that's going down 3. So when this shifts the graph, it's also going to shift the asymptotes. So my vertical asymptote is going to shift left to x equals negative 2. And if you think about it, that value makes sense. Because if I plug in negative 2 for x, I'm dividing by 0, which I can't do, which is why there's an asymptote at that point. Horizontal asymptote, that's also shifted down. So I get y equals negative 3. Now, this graph is going to have the same shape as the parent function. So it is, when it comes to sketching these rational functions, the specific points are not nearly as important as if the asymptotes are correct, the intercepts are correct, and then that we have our graph drawn in the appropriate places in relation to those asymptotes. So kind of similar to polynomials, where kind of what was happening in here wasn't as important as what's happening at your intercepts and what's happening kind of near those asymptotes. So to help us with that, the Schoology notes had this already placed on there, but I didn't edit this page. We're going to also look at the y-intercept. So to find the y-intercept, for every function we ever look at, you replace x with 0. Well, if I replace x with 0, then I get 1/2 minus 3, which is a negative 2.5. So my y-intercept is 0, negative 2.5. That also helps us see where our graph is going to go. So typically the way these graphs kind of work out, if you notice, there's kind of like 4 quadrants here. And we kind of need to figure out which quadrant our graph is going to go in. And we'll look at this again a lot more on Friday. But for now, the shape is going to be similar to the parent function. The parent function had one curve kind of here in the top right, and then it had another curve down here in the bottom left. Now, again, the specific points like around here are not as important. We need to make sure our intercepts are accurate and that we've drawn these curves in the right places. The other important part, again, is the asymptotes. That's a really important part of this graph. All right, so now let's look at the domain. So again, this domain, it's restricted by the vertical asymptote. So vertical asymptote will restrict the domain on our graph. Range will also restrict the domain on our graph. I'm sorry, I just said range. Holes will restrict the domain on our graph. The holes, when we find those, will restrict domain. Range, actually today range is really only going to be affected by the horizontal asymptote, but once we get into these more complex graphs, range is going to be very, very different. So we can't really rely on this same kind of pattern. All right, so now we're going to look at what happens as the x approaches -2, and that little plus means from the right side. So I look at -2, and then I look at the right side. So as that graph gets closer to -2 on that side, my y's are approaching infinity. All right, let's look at our next one. Transformations, this graph has gone right 4, up 2, and it has been reflected over the x-axis. So that means the shape of this graph is going to look different. Now, one thing that is nice about these, if I reflect this graph over the x, or if I reflect it over the y, it's going to look the same. So whether or not you flip those, it's actually going to still work out. Because of those transformations, vertical asymptote is x equals 4, horizontal asymptote is y equals 2. And again, because it's reflected, it's going to go in these quadrants. Your intercepts will also help guide you to that. We'll talk on Friday about how to find the x-intercept, but for today, to find the y-intercept, if I plug in 0, that's a negative 1/4 plus 2, so that's 2 1/4. And then again, that fits with where I drew my graph in relation to those asymptotes. Domain is -infinity to 4, and then 4 to infinity. Range, -infinity to 2, and then 2 to infinity. Then we look as x approaches -infinity. Well, as our x's get smaller, our y's are approaching 2, which is the horizontal asymptote. All right, so the last two that we're going to look at is we are just going to look at a function that looks more like the format we're going to see on Friday, but again, they'll be a little bit more complicated. But this is a pretty basic rational function still, but what we can do is by using division, we can actually rewrite this into the form we just saw in order to see those transformations a little bit clearer. Because if you think about it, division, okay, and that fraction bar kind of mean the same thing. So I can do 3x minus 2 divided by x plus 4. Well, since it's x plus 4, I can use synthetic division. And if you remember, the way we write our answer for synthetic division, we start 1 degree less. So 1 degree less than 3x is just 3. And then we write the remainder as a fraction over the divisor. Well, now this is in a format pretty similar to what we just did. Now, this is not the way we are going to graph these functions going forward. Okay, this is just, I want you guys to kind of see how it corresponds to division and just understanding, again, those transformations. But we are going to graph this using a different process come Friday. The reason we're going to do that is because this process does work well when you have kind of a linear function in both the numerator and the denominator. But when you get into quadratics and cubics and higher order functions, this process doesn't really make it much easier to graph. All right, but using this, we can now see that we have a vertical asymptote at -4. Horizontal asymptote at y equals 3. This graph has been reflected, so it is kind of going to be in these quadrants. But let's go ahead and get our y-intercept. Y-intercept is way easier from the original. If I just plug in 0 top and bottom, I'm left with -1/2. So I can see there's my y-intercept. So I'm going to have one curve in this box and one curve in this box. All right, let's go ahead and look at this last one. We'll do our synthetic division. The remainder, again, we write as a fraction over the divisor. So our vertical asymptote would be at 3. Horizontal asymptote would be at -2. That graph's been reflected. And then let me go ahead and write the y-intercept. I didn't go through it pretty close, but if I plugged that y-intercept in, I would get 1/3 as a y-intercept. That would give me another accurate point. All right, so the last thing I want to show you guys is just how that vertical stretch, whenever we look at this, actually affects that graph. You'll notice whenever we graph these, by changing your intercepts, that's going to you'll see that effect pretty clearly. But I do want you guys just to see an example here on Desmos of how adjusting that stretch actually makes the graph look. Okay, so right here you guys can see, here's your rational parent function. As I move h, okay, that's changing my vertical asymptote. As I move that k, it's changing my horizontal asymptote. Now notice, again, typically we're not going to see this outside value whenever we get to the rational functions we'll see later on. Typically it'll all be just one numerator and one denominator. But again, I wanted you guys to see how it affects it. Well, now let's look at that a value, that stretch. As I make it bigger, you'll notice what it's doing is it's stretching it away from really that intersection of those asymptotes and pushing it farther away. When a becomes negative, it reflects, and again, as it's larger, it is stretching that graph farther away from where those asymptotes intersect, and that's what that stretch is going to look like. Now, for the sake of what we're doing in here, what's important is that you get the accurate intercepts. I'm not going to be as concerned about getting all of these little points in here correct and how the difference between them is. By getting your intercepts correct, that will make it clear how your graph has changed compared to some other graphs. And notice as we change this, it changes your intercepts, okay? All right, so that is it for rational functions. We will look at, again, like we said, some more complex examples on Friday.